So this is a beautiful problem, and this is called power required in pulling a rope. So problem says, figure shows a rope resting on rough ground. One end of a rope is pulled by an external force such that it moves at a uniform speed v. If the mass per unit length of rope is given, and that is lambda per kg meter, lambda kg per meter, we have to find the power associated with the external force pulling the rope. Assume there is no slipping of rope on the ground. So what we have in this case, a force is applied. So this is the force that is trying to pull this rope, and some part of this rope is on the ground and some is basically pulled. Now lambda is given, that is mass per unit length is given, and it is also given that this moves with a uniform speed v. So speed is given uniform, and this ground is not smooth, so this has some roughness, so mu is not equals to 0 in this case. Now let's say some force F is applied here. Then we have to find the power associated with the external force pulling the rope. So we have to find power associated. So what is the power that is required to pull this rope? So basically we will solve this problem by two methods. First, let us discuss the first method. If you remember, power is what? Power is nothing but F dot v. And in this case, force and velocity both are in the same direction. So I can simply write force times velocity is power. You also remember work energy theorem, that a change in kinetic energy is equals to work done. So change in kinetic energy is equals to work done, delta W. And work done we can also write F dot displacement, that is dx. And let us say in this case both are in the same direction. So I can simply write delta K is equals to F dx. Or if you have very small, then you can simply write this is delta x and this is also delta x. Now if you differentiate this with respect to time, so rate of change in the kinetic energy, we can write F dx by dt delta x by delta t, and if time goes to 0, so in the limiting sense I can say dk by dt is nothing but f times v, because dx by dt will be velocity. So we have to find power. So this term we have to find. So basically power is nothing but dk by dt, because power is f dot v and f dot v is nothing but simply dk by dt. So somehow if we can calculate rate of change in the kinetic energy, that will be the power transmitted or power associated for this movement. So let us first find this kinetic energy. So at any point of time, what will be the kinetic energy? So kinetic energy is half m v square. So let us say this mass that is here, so this mass is moving and all part is moving with the same velocity. Velocity is v. So this is given in the problem, velocity is v. And let's say this length has a x unit length. So from here to here length is x unit. So what we can say, mass is simply lambda times x, because mass per unit length is given. So in this case mass will be lambda x. So kinetic energy will be half times lambda times x v square. Now if I differentiate this, that is a rate of change in the kinetic energy, this will be simply half lambda dx by dt, and this multiplied by v square. And dx by dt is what? Dx by dt with what rate this length is changing, and that is velocity. So this dx by dt is nothing but v. So we can simply write half times lambda times v square. So this is half lambda vq. So this will be the power transmitted in this case. So there can be an alternative method. So let us try to see this alternative method also. So we can have an alternative method. So now let us say initially this was the situation, and since you are pulling this, so rope will, so this part of this rope, this part of the rope has gone up, and then this is also moving. So what we can have in this case, so we can say this was the situation, initial situation, and this is the final situation. So we can say this part of rope is basically that has come from the ground. So let's call this part of the rope is dx, and this part of rope has basically come from the ground. Now you see this dx, so this is extra dx, so this will be dx by 2. So this distance will be what? Dx by 2. This is because this dx by 2 plus this dx by 2 will basically generate dx. So on the ground only dx by 2 part, so only this part, of rope has gained some velocity v. So this is very important. You see here you have a dx part, but this dx part contributes from two things. One is dx by 2 that was already having some velocity v, and this was having no velocity. So this part has gained some velocity, and this velocity is v because question says the rope is moving with a constant velocity v. So we will use here force is equals to, that is Newton's second law, force is equals to rate of change in momentum, dp by dt. Now only this portion has gained momentum. And what is the momentum? Momentum will be, so we can write, so this momentum will be, P will be m times v. And what is mass? So lambda times dx by 2. So this is mass. And what is velocity? Velocity is v. So we can say momentum is lambda v by 2 dx. So this is momentum. So this is the gain in the momentum. So what is the change in momentum? So we can say, so this, let's call this is a small dp. So this is a small amount of moment that has been gained by the small dx mass, basically dx by 2 mass. If I differentiate this, then I will get the corresponding force. So dp by dt, so let us differentiate this. So both sides we can differentiate this. So this will be lambda v by 2, and dx by dt is nothing but v. So we can say dp by dt is nothing but external force is equals to half lambda v square. But what we have to find? We have to find power. So how much power is given? So power is nothing but force times velocity, and force is nothing but half lambda v square and times velocity. So this will be half lambda vq. So this is the power given to this rope so that this rope will move with a constant velocity v. So this concludes the video. So only one important point you have to think yourself, that only dx by 2 portion of this has gained some momentum, and that is moving with velocity v. So even though you have considered dx, but only dx by 2. You can also do this by constraint method, that is you can basically see the length of the rope, and then again you can come with the same conclusion. So I hope you enjoyed this video, and if you enjoy, please share with your friends, and you can also subscribe to my channel, and you can share this video to your friends. Thank you.